Good morning, everyone. My name is Omkar Maslekar, working at Intel at software engineer. I am here with Jingjing. Jingjing, you want to introduce?
Yeah, I'm Jingjing from Intel and also the software DPDK software engineering, and we cooperation each other to implement it about the DPDK Polling Mode driver for no transparent bridge. So this is our topic. So Omkar, you can go first.
Yeah, thank you. So for the next 30 minutes, we are going to introduce the DPDK PMD for non-transparent bridge. Let's get rolling. So legal disclaimer, just flashing with some of the hyperlinks here. Would like to start with the acknowledgement, as some of the key folks are present here. Gentlemen, can you raise your hands? Keith, Edwin, and Shuming. Yeah, would like to acknowledge them with the big round of applause. So for the next 25 minutes, I will introduce the NTB along with some of the use cases. We'll deep dive into the device, because for some of those, it could be a new device, never heard of it previously. After that, in the mid sections, we'll deep dive into the poll mode driver from the DPDK's point of view, how the queue is implemented, how efficiently the queue is implemented. And finally, we will talk about the performance, ending with summary and later Q&A. So one question to audience, like how many of you never heard of the NTB? Okay, quite few folks, okay. So this is the good slide to start with the NTB. I will just give a very brief overview what Intel NTB is. It connects, if I have to describe in very simple terms, it connects two systems. So that's what the picture says. And the term non-transparent, meaning it follows the PCIe semantic, but the other end of the PCIe endpoint is not visible. That's the reason it terms as a non-transparent. So it used for the low latency transfer. While low latency transfer, it is crucial because whenever you are exchanging the data between the systems, you have to follow the NTB semantics. I'm going to introduce some of the concept, what are those semantics in terms of NTB. And another main advantage of using the NTB, it comes free. So it's low maintenance, and you don't require any special hardware to enable it. So all the Xeon platforms having the NTB device. So only thing is you need to enable and get benefit out of it. So on the current processor, it supports the 3 NTB devices and performance up to on the 16 gigabyte per second for the current hardware. So from the previous slide, we just show the diagram of how the two systems are connecting. Now let's talk about in terms of some of the PCIe language or more in depth of the hardware. So every CPU has the root complex. Root complex as having the multiple root ports. So one of the root port is getting converted into the NTB port. So that's how you enable the NTB on your platform. It doesn't require, as I mentioned, special hardware. It's available. And for the forwarding, so how these two servers are talking to each other, it's just forwarding some of the transaction from one system to another systems with some address translation. Address translation is I'm not going to touch more in depth in this session, but introduce some of the concept of read and write for the in terms of like shared memory. And on this diagram, there is 2 NTB devices. So on the left-hand side, the NTB device, it's connected to another system. So this is one of the popular combinations and known as the back-to-back transfers. In this section, we will cover some of the current use cases and how it is widely used across the industries. So whenever you have the large in-memory databases, so typical for the comms database, it is IMS core having the home location registry. That is one of the popular database that can resides in memory. So and whenever you have application where you would like to have the high availability and data redundancy, that is the another use case. So and for dual node enterprise storage array. So most of the storage arrays, it can be dual node or the quad node. So whenever you have some stream of data coming into your server without processing or without storing on the drive, you would like to replicate because you don't want to lose that stream. So you can duplicate that stream of data on the another server. And control application, of course, for the current use cases are for the mobile. It's related for the WAN sensor and actuator sensor network. This list is growing. This is very minimal subset I would like to highlight here, because whenever you have the application that is taking large footprint of the memory, that can get benefits of using the NTB. So some of the checkpointing thing, or you have the lots of like VM container running the things, and you would like to log somewhere into the second system, or don't want to lose the from the primary server. So that can be backed up using the NTB on the second server. So here I'm going to introduce the concept of the shared memory. It's with the NTB system as from the previous slide. The diagram is exactly same, but for here on the server one, the NTB device is connected to server to NTB device. So as I mentioned, this is back-to-back transfer. So on the outer side, whenever the server one is initiating transactions, it's land into the server two. So that's what the outer arrow says. And again, the inner arrow communicates with the server one using the remote memory. So this is the concept of the shared memory. And how the transactions are initiated, I'm going to talk on the next slide. But as I mentioned, each server is having 3 NTB devices. So why don't we get benefit out of it and create some topology sort of like, if you want to cascading the server, or you want to implement the tree or the bus or the ring topology within your data center, or inside the rack. So this is what the diagram indicates. So if the server 3 is connected to the server 2, but keep in mind that server 3 is not having the NTB device. That's fine, means it can be having just a server with storage, or that can get benefit, because the advantage of using the NTB, server 3 can see the other endpoint, that is the secondary endpoint from the server 2. As I mentioned, there is concept of shared memory and how the semantics of the NTB has to be followed. Here is a small animation I will run for you, and we'll introduce the concept of remote write and local read. So you have the piece of memory between the two systems, and that memory is accessible from both ends of the system. So how to get the best performance, this diagram indicates. So server 1 on the left-hand side having the NTB device, again the configuration is back-to-back. Whenever the transaction is initiated, it considered as MMIO transaction, standard MMIO transaction. So some of the performance benefit from getting from the MMIO transactions are, you can classify that as write combining, and it is uncached. So you can initiate one heavy big fat transaction instead of sending the small transaction out of the server 1. And whenever 2 devices are exchanging data between 2 systems using the NTB devices, that is classic PCI transaction. And of course, on the second server, it is DDIO transaction. So by default, it is enabled. You don't have to worry about anything. So any kind of IO transactions directly land into my last level of cache. So again, these are some of the performance tuning we implemented to get best performance out of it. So on the left-hand side here, it's the concept of the remote memory. Server 1 is writing directly into the remote memory of the server 2. And server 2 is reading from its own local memory. So following the conventions, you get best performance out of it. If you break the semantic, you may run into some of the performance issues. more about the NTB device details, because for folks who are not familiar with NTB devices, so this is a good slide introducing what it gives. It is general PCI device having its own config space, and two important aspects here, what the bar 0 and bar 2 indicates. Bar 0 is configuration registers. It can have doorbell registers as well as the scratchpad registers. The previous animations on the previous diagram I showed, that is classifies as the memory window. So we implemented all three inside the DPDK, but doorbell registers are useful for sending the interrupt to the other side, and the scratchpad registers are used for sending a small amount of data between two sides. But the memory window can go from 4 kilobyte to 256 gigabytes. So if you have the database requirement in terms of like terabyte, this is one of the good candidate for sending the data across the system. So bar 2 and bar 4, we get the memory window out of these two bars. So you can have sender receiver or NQ DQ implemented from this bar 2 and bar 4. So this is classic memory window example. So with this, Jingjing will talk more about what's inside the DPDK package from the NTB Poll Mode driver point of view.
Okay, thanks to Omkar for the sharing about the NTB hardware devices attributions. So now I'm going to talk about how we enable this device in DPDK by our software. So let's have a look at this picture. As we know that DPDK has a kind of device called a row device. It is abstract of framework to support multiple kind of device to avoid introducing some change to libraries or EALs. So we put the NTB kind of device here, and because NTB device is not just specific to Intel, it is a kind of PCI spec. So multiple vendors can support no transparent bridge. So we define some ops for the NTB kind of device. To be a row device, we need to follow this row device API, such like device configures, device started, and enqueue and dequeue functions. To be an NTB device, as the previous slide said, that the memory window, doorbell, SPAD registers is a common thing. So there is some ops to define for these operations. From this framework, we can see that with this design, we can introduce the NTB kind of device from the memory access to a kind of packet I/O interface. So if you want to use the NTB device in DPDK framework, so first you need to, after the driver props, the link is up, and then you need to configure the device. These three functions need to be called in order. This is similar as other kind of devices. Get the device info, and then configure it, and then set up queue, and then start. After that, we can call the enqueue and the dequeue functions to receive and transmit packets. At the meanwhile, statistic functions also provided to show the hardware statistics, such as how many packets is received and how many packets is sent. Then let's go deep to the how the device is set up and which information we need to communicate with each other. For example, server A and server B is connected with each other by the no transparent bridge. So when the driver is propped, the driver would be try to set up the device, and but another side maybe it's not up. But when it is up, the physical maybe the handshaking happen, negotiation is happening when the link is up. Or we also need to take some device attribution to sync with each other, such like how many queues we support, which is the queue size. and how many memory window it is support, and what is the memory window size, what is the local memory address you are going to map to each other. So after that, the device can be ready for transmission. This is all, those things are all done in the device config operations. So we already know that the device is configured, but what is the ring looks like? So we need to get the no transparent bridge for packet I/O to be better performance. We need to go to deep about the device and go to the deep about the CPU. So as the previous slides, the Amir said that the PCI transaction write is posted, and the PCI read is non-posted. So the latency might be different. And from the CPU perspective, we also have a kind of memory type, what is uncacheable and it cacheable and it is write combined. Because NTB is a kind of memory mapped device, so we can set that to be a write combining type of memory. And we can see from the right picture, if we set the memory to be write combining and use the instruction to write and read 16 bytes of memory, the latency of the remote read is more than 30 times than the remote write. So this is the hardware specific features, and then we go to when we design a ring, what we need to provide for the buffer address. The transmit side needed to get to know where I need to transfer to that. Where I need to transfer to the packet, and the buffer length I need to know the size the provider the peer provided to me to transmit. For the TX write back, things is tell the transmit side what is the status of the transmit. For the X write back information, such like I need to know how many how long is the packet. The receive side needed to know that. TX tail index, the transmit side needed to update that to tell the peer where is the TX traffic, and the X tail index, the received side needed to update it to tell the peer where you can send, where the buffer is ready for you for me to receive. So compare with two left side and the right side, the first thing to our mind is like we need to avoid all those read operations to avoid them to be remoted. So the next thing is like Intel CPU, or we can see that x86 has a better ordering for the memory access. So if the memory copy is done by the CPU, and we can update the TX tail after the memory copy. So if the TX tail index is updated, that means the packet is already sent. And in our case, there is no additional TX write back information in our NTB dequeue functions. So I think this TX write back information can be omitted. Yeah. So now this is our ring design for this NTB device receive and transmit. So we can see that the descriptor ring, which contains buffer address and buffer length, will be located in the transmit side, while the receive side X write back information, which contains the packet length or some flags, will be located in the receive side. X tail would be located in the receive side, and we put the TX tail to the receive side. Here is very simple sequence for the in-queue sequence. For example, at first, when the transmit side needed to transmit a packet, it needed to check the IX tail and to see whether any buffer is ready to copy to. So it gets the descriptor and the buffer, where the buffer is located, then copy the packet to that buffer remoted. After that, it needed to write back information to the receive side about how long the packet is, and then update the TX tail. That means all the packet is transmit success. Another easy way to understand the Dequeue sequence is like the CPU of receive side check the TX tail and find the packet is received and check the IX write back information to get the buffer packet and the packet length. The packet is read from that buffer to the buffer. The CPU is read the packet. After that, the CPU of the receive side will need to locate a new M buffer for this descriptor ring to next maybe packet transmit and receive. At last, CPU on receive side needed to update the IX tail to tell that I'm ready to receive another packet. So the dequeue and in-queue functions are very simple here, but we did a lot of optimizations. Who are familiar with our XTX burst functions, there may be some threshold things and bulk log things. We also did that part in our NTB Polling Mode driver. So this is the performance we get from our benchmark. We connect to the CPU by the NTB adapter and using the NTB forward applications. One server is just for sending, another server is just for receiving. So we can see that when the buffer size is increasing, it almost clear, very near to the PCI bandwidth. And when the buffer is increasing maybe to 256 bytes, one core most enough for the transmit for the packet for the data move. Okay, let's go to check where is the code. So for DPDK release 1908, we already introduced this kind of device. It supports Intel built-in non-transparent bridge, and we already contribute a sample which supporting the file transfer. Incoming release 1911 and the queue design, in-queue, dequeue, all the things are already being merged into a master branch. The sample is also extended to support the packet forward. So all those code already been merged in the master branch. You guys can download and have a look at it. Okay, at last, I think we need to summarize our talk today. Today, Omkar introduced the Intel Z platform and for the non-transparent bridge. It is a built-in device in the Xeon CPU, and this is the first type of NTB device in DPDK, and we designed an efficient ring for the data movement and reached the PCI bandwidth limitation of the Gen 3 plus 16 adapters. Okay. Okay, thank you. So, any questions?
Thank you for the very good presentation.
Thank you.
I have a question. You show performance numbers and you show bandwidth, actually, over PCIe. I'm asking how this method of passing data between servers compared to other types of transfers, like using network or RDMA. Do we have some information regarding latency, for instance?
Okay, for the latency, we did some tests. Right now, it is about maybe a few microseconds for the latency part.
Yeah, hello. I measured some of the round-trip latency numbers. So if you follow the semantics of the NTB, so for example, if you're writing into the remote write and local read and measure the round trip, it is less than 1 microsecond. So in terms of like nanosecond, I would say.
Yeah, you mean the for the packet?
But if you don't follow the semantic, you may get some of the bad performance data in terms of latency.
Yeah, you know.
Semantics are important.
You know, the performance is, latency is always computer is at each other, right? So maybe here is the performance number right now. So we also tried to test this latency, and we get the few microsecond on that design. But if we needed to tune about the latency, so maybe we needed to change the ring size or something else to achieve that part. Right now, we just focus on the performance. Yeah. Thank you.
I have two questions. One is, what's the security model of this? Do you basically assume both systems completely trust each other?
I think this NTB transparent bridge is connected to different system, but I don't think this is a security insured design for that platform. Okay.
Yeah, just it's the memory sharing. And then the other question is, what happens when one of the systems dies or the link gets pulled?
Sorry?
So if the other system goes down, it has the link status control that immediately turns that, hey, my remote host is down, kind of.
Yeah, but all the outstanding.
And you can communicate in terms of like doorbell interrupt or some of the status bit in config space, I think they goes off. So
I was more concerned with all the outstanding transfers and trying to recover those, and reference counts of those is a very hard problem. No, but it's how do you recover the buffer? The recovery process is very difficult. Right, but it's more that if I'm transferring to another machine and that machine's potentially dead, or maybe it's not dead, you need to have a synchronous response that says, yes, it's really dead. You can now free those buffers. Yeah. Right, say timeout on the right back. Yeah, okay.
Hi, thanks for the talk. So about the security, I think we can use something like IOMMU, so protecting one machine from writing the memory to the remote one, right? So at the local host, you can, NTB is also a PCIe device, so a local machine can program IOMMU, so saying that for this address writing to my local memory, what's the allowed address and what's not allowed. I think I tried that before, but not using the Intel NTB. So a question I have is that you mentioned about packet transferring and throughput, right? So does NTB support packet metadata? For example, usually packet needs to have something like checksum of low or segmentation of low. So in your number, is it having that metadata, or it's just a buffer copying, not packet throughput? Thank you.
Because the no transfer bridge device is just designed for the memory access, so there is no additional offload for the packet processing. So the metadata may just including the length and maybe NO packet, such things, no checksum offload. Yeah.
Okay, I'll go first. I have two questions. One is how does it scale? So, I mean, how many machines it can be bridged together? And the second question about, can we, from one side of the machine, can we abstract the API into just memory? That means if you do a move instruction and the operation will go into the other server. So can we do that kind of API? So just memory from one side.
For the first things that maybe for the connection, maybe scale to multiple server connection, maybe we need to introduce another PCI switch and to connect to different. Or currently, how many NTB devices support the Xeon platform?
3 devices per processor. So for the dual system, you get like 6 NTB devices.
Okay.
Yeah, otherwise we needed to introduce the switch.
Okay.
Yeah. For the second question, for the memory access, because the task here is for the DPDK. You know, DPDK is high performance, maybe like software. So we are going to demonstrate the NTB performance data for the packet I/O, and this is the DPDK, which is focused on data plan packet processing.
Okay.
Yeah.
Okay. Thank you.
Yeah, question? I think what you show here is a enqueue-dequeue semantic over the NTB. And as mentioned before, the same can be achieved both in latency and bandwidth term with RDMA. The question is, do you have thoughts to expose also load store semantic on top of this NTB so that you can have more easy programming model for the user?
Sorry, okay. Did you get the question?
Sorry, I'm having difficulty understanding your question. Can you repeat the question?
Yeah, so if I understand correctly, with the NTB, you can map some PCI address space to other hosts, so that every load and store to this area will be tunneled to the other host. And you wrap it up with the NTB PMD with enqueue-dequeue semantic when you manage the queue, receive and transmit. So the question is, do you have any plans to expose an actual address space to the user that it can just do load store to these addresses, and those load and store will be tunneled to the other hosts?
Yeah, maybe I can try and address that. So the answer in short is it's, so this is NTB, right? So it's a PCI Express range that gets mapped. It's difficult to do load and store operations because you'd have to go and read back the data, right? And read back the data is really, really expensive. So while we could do it, if you have two NTBs that are mapped back to back, then you can do it because each have visible to its own memory. But there is a catch to this, because when you read remote memory, like like you said earlier on, it's a posted operation. So you have to wait for that response to come back. So what Omkar was trying to tell you is, don't do that, because that posted operation is really, really expensive. So if you really want to do load and store kind of operations, you can, but it comes at a performance cost. So our guidance is, don't do that. Utilize the write routines from either side to acknowledge your data. So we don't have any immediate plans to post those, to post patches to do that. But if there is interest, we can certainly go look at that. So does that make sense? Yeah. Other question I wanted to address was around latency. So the latency is actually really good. It's about 700 or 800 nanoseconds for a remote write to complete. And the reason why that's so fast is we do this, the platform supports DDIO, so we can actually write into the last level cache, right? So you issue a write, it gets sunk by the root complex, goes over the wire, and then on the other side, we actually push it right into the LLC. Right? That's why we get that, really, really fast latency. And I think there was a question about security. So it's a completely separate PCI Express subsystem. It's not immediate. It's not. It's secure as your root access is, right? So that's kind of how that works. I think there was one more around. Let me think. It'll come to me in a minute. Sorry.
Thanks,
About 800 nanoseconds, 800 nanoseconds, about 1 million samples or so.
Hi. So what are the future plans for supporting Pass ID and SVM in the scope of NTB? How it will handle that once the PCI transactions are probably going to look a little bit different?
I think this is a part of PCI roadmap, right? So it is about our maybe CPU platform for the passive ID supporting, and our device that may not related with the NTB part right now. Yeah.
But if the root complex now expects specific transactions, you're supposed to adapt to it. So the question is, is there any roadmap in order to support this in the future?
Okay, sorry, I have no such idea right now. Yeah, sorry about that.
Yeah, maybe I can address that. So what Jingjing is actually saying is, today, so to be clear, right, I don't think today we actually front the NTB with an I/O MMU. So there is no I/O MMU there, so you get to see the remote bar, and that is what you write to. That's the way it works today. In the future, I believe there are plans to put an I/O MMU in place, and then you get automatically PASIT support, which will support in the near future.
Hi, I have a question related to performance. What is the performance difference that you guys see with and without PMD for NTB?
Sorry, can you?
What is the performance difference that you see from NTB supporting DPDK and non-DPDK?
Okay, NTB, I think there is kernel supporting for NTB device. It is built up a net dev for that kind of device. So when we do the benchmark, that our performance is much better than that part. But if it cannot reach the PCI, it cannot reach the PCI limitation. Yeah.
Any performance, like a percentage variation for 64-byte packets from kernel mode to DPDK mode? What are the improvements that you see with PMD?
So if some of the micro benchmark shows whenever there is transition between the kernel and user, takes anywhere from, depending upon what activities are active inside the kernel, may take around like 4 to 8 microseconds. If you are using what kind of mechanism passing data from the user to kernel. But in terms of latency, this is the best because you are polling on that particular address.
Sorry, it's about it's like 30x. The NTB, when you map NTB into a socket, you map it into Linux, and you have the usual user kernel to user space transitions, and like I mentioned earlier on, if you need to do a remote read, which is what a socket does to check for completions, the performance is really, really bad. It's in the order of 30x.
Oh, okay. Thank you.
Okay, no more question? Thank you.
Thank you.